Hi all, this is Dr. Knapp. I just finished looking over your guided notes for chapter 1, and I wanted to make sure that I pointed out a few things to you. There were some things that either you seemed to be missing or that seemed to be unclear for some of you. So I want to make sure that I hit those points and that you have them corrected in your notes so that when you see things on your exam, you are able to get the correct answers. So I've made a little PowerPoint that looks at some of the different points that I wanted to highlight. So let me pull that up. So this is all over chapter 1, and I will try to do something similar for chapter 2. So one of the things that I wanted to look at was the particle view of matter. And that is something that is really important both in this text, but also in understanding what's going on at a chemical level. So the first thing is to distinguish between atoms, molecules, and mixtures and compounds. So first of all, note that when we have an element, we only have one kind of atom. Now here, those are illustrated by different colors, but atoms are really a lot smaller than a wavelength of light, so they don't really have individual colors. But when we talk about an element, it could be just an individual atom. That might be something like helium, or it could be molecules that are the same element bonded together. So nitrogen is N2, oxygen is O2. They are what we call diatomic elements. And so that's what's illustrated in B here, the yellow diatomic elements. On your list of molecules to know, there are 7 diatomic molecules that you should be familiar with. So when we talk about them throughout the semester, then you will remember that, okay, anytime I hear about oxygen as oxygen gas, I'm really talking about O2. I'm not talking about an individual atom of O. A compound is going to have the molecules stuck together, like you see in C here, and all of the molecules are going to look the same. So you see every one of those little particles has a black atom at the center and a light blue atom surrounding the center of the atom, the center of the molecule. So compounds can be separated chemically because we can use a chemical reaction to break apart those molecules into the individual elements or into different molecules. So something important to remember with a compound is that the atoms aren't just near each other, they're stuck together by what are called chemical bonds. And we'll learn more about those in future chapters. But the blue and the black atoms here in C are actually sharing electrons, and they're not going to wander away from each other unless we do a chemical reaction. In contrast, in D, we have a mixture. So we can see we have all the different kinds of particles, the individual atoms, the diatomic molecules of the elements, the compound. And so when we have different elements in here, it's not just that there is more than one element, but that each particle might look different from the particles next to it. So a mixture differs from a compound because not all of the molecules are the same. We have different kinds of molecules. And so using physical processes, things like boiling or filtering or evaporating off of a liquid, we can separate out the molecules of one kind of substance from the molecules of another kind of substance. So those are the distinctions that we make. One of the things that I also asked you to do was to talk about the particles of gases, liquids, and solids. Now, most of you talked about how closely they were packed together, and that's an important starting point. It is also important to think about how fast the molecules are moving. Now, we can have motion in a couple of different ways. So vibration is a motion where the molecule doesn't move around. It's just wiggling in its spot. And so some of you said that solids can vibrate but not really move around. And that's a really good description of that. And so because of that, solids are going to keep their shape. Each individual molecule, as represented by the circles here, cannot change places with other molecules. They're going to have a shape. They're not going to have gravity spread them out. And so that's why they remain solid. A liquid, on the other hand, is going to take whatever the shape of the container is. And so the molecules, they don't really separate from one another. There's a little bit more space in there, but just enough space that they can move around one another. Unlike with the solid, they're packed so tightly that an individual atom can't really exchange places with another atom nearby. We've got enough wiggle room in the liquid that it can vibrate, but it can also move around within that liquid. It can do what we call translate, move from place to place. And so because of this, the liquid shape takes the shape of its container. So when we're looking at these particle views, liquids and solids will show the particles touching one another, but we can tell the difference in two ways. The solid will typically be more organized, though as we talk about amorphous solids, we're going to recognize solids aren't always highly organized, but they're typically more organized. And a solid in the particle view may show that it's not spread out across. And notice that the liquid all the way across the circle there, it's pretty level. But with the solid, there's sort of a drop off about 2/3 of the way over. So that's showing it's not filling or taking the shape of its container. It's not filling it to the sides. Now, the gas is what we typically show pictures of when we're trying to show molecules so we can see them individually. If we try to show the molecules in the liquid or solid state, it can be hard to distinguish one molecule from another. So molecules, because they are so spread out, they are less dense, almost 1,000 times less dense than liquids or solids. And because they are less dense, they're able to fill their container. This is because the molecules aren't as strongly attracted to one another, and so they're not going to pull each other down and condense on the bottom. So we say it's a non-condensed state. Now you'll notice there's also a couple of lines outside of each circle there. That's to indicate that they're moving very, very quickly. So relative to solids and liquids, the molecules of a gas move very rapidly from place to place. They translate very rapidly from place to place. Okay, so those are things to keep in mind, that I'm not just going to talk about how tightly packed things are, but I might ask you a question about whether something fills its container, or why does it fill its container. I might ask about whether it is condensed like a liquid or a solid, or not condensed like a gas. And another term we kind of use is fluidity, or whether it flows. So both gases and liquids are fluids because the molecules can move relative to one another, but the solid keeps its shape so it doesn't flow. All right, so then there was the question about mixtures, or distinguishing between different kinds of mixtures and compounds. So solutions on a macroscopic level, you might not be able to tell something is a solution just by looking at it. So if we look at this instrument down here at the bottom, I think that's a French horn. You might say, well, that looks like it's just one kind of element. Everything looks kind of that gold color, so perhaps it is an element, or maybe it's a compound. So you have to know a little bit more about what's going on there to know that it is a solution. So some of the characteristics that you're going to see is that a solution will typically be see-through or transparent. So the sky, I'm just looking at the sky over here and not worrying about the plane and the trail going behind it. That's just to illustrate that we're looking at the sky. The sky is clear. We can see through it. Water is clear. We can see through it. These things in the flasks are also clear. They have color, but we can see through them. Okay, so solutions we can see through if they're in one of our fluid states, because air and water tend to be see-through. And so that means the particles are mixed well enough that we don't have big chunks of particles deflecting the light. Now, our instrument here is made of a metal, and metals, when they mix together, can make solutions called alloys. And so you would just have to know whether the metal was a mixture by knowing whether it is something that appears on the periodic table or doesn't. So this is a brass instrument. And if we look on the periodic table, there's no element brass. But if it's a metal and it's not on the periodic table, it's pretty much going to be a solution. There are some exceptions to that, but for our general purposes here, we can either have a metal like copper or zinc, which is what brass is made of, or I can have a solution, which is a combination of two or more metals, combination of copper and zinc. And they tend to just mix together the same way that fluids would, and then they, once they've cooled down from the molten state, form the solid. Heterogeneous mixtures, on the other hand, tend not to be see-through. So sometimes I call them chunky. So if you look at a chocolate chip cookie, it's really clear that I have some spots where there's chocolate and I have some spots where there's no chocolate. So different parts are going to look different. But when we're talking chemically, generally we're talking about things on a much smaller scale than a chocolate chip cookie. So if we look at something like a cloud, it has more than one phase. It has liquid water droplets. There's also ice in there as well. And then there's the air. And so the ice and the liquid water mixed in the air are going to diffract or deflect the light so that we can actually see where the cloud is there. In milk, we have fats and we have proteins and we have sugars. Now, the sugars mix pretty well with the water, but the proteins cluster together, the fats kind of cluster together. And so that's why we can't see through milk. Now, if we take something like this pond water here, normally when we think of water, we would be able to see right through it as if there was almost nothing in the way. But we can see here that the scenery behind that bottle is not as evident. It's kind of cloudy. And if I said, well, why don't you drink this water? You might say, there's something in there. So when something is cloudy, even if we can kind of see through it, that cloudiness indicates that it's a heterogeneous mixture. Okay, so mixtures can be separated by physical means. We don't have to do a chemical reaction. So we talked about evaporation, filtering, or like in the case of the chocolate chip cookie, I could just pick out individual chocolate chips. And then mixtures also can have any ratio. So in our picture of the compound, we had 1 black atom to 3 light blue atoms in every single case, the same ratio. But in a mixture, I can have lots of different ratios. So think of tea. Now, I grew up in Indiana. If we had sweet tea, you would have a little bit of sugar in it and be barely sweet, which is why I didn't grow up drinking tea. But in the South, depending on where you're going, you might have something that's, sweet like a soda, or you might have something that's almost syrupy sweet. So we can have very different levels of sugar in there. All of those are considered solutions. They're all mixtures, but they really have the same components. It's just how much sugar is in there. Similarly, if I have coffee, I like to say I have a little bit of coffee with my cream and sugar because I really just like the smell of the coffee, but I like the cream and the sugar. So my coffee is mostly cream and sugar with just a little bit of coffee. My brother-in-law, on the other hand, likes his coffee black, and he maybe puts just a little bit of sugar in there. So even though we might have similar things in the coffee, the ratios are very different. All right, so if we think about each of these things, you might pause this video here and ask yourself, okay, can I tell whether this is an element, a compound, or a mixture? And if it's a mixture, can I tell what kind it is? So we talked about air, that's a solution, which is a kind of mixture because we can see through it. Oxygen is an element. We can find it on the periodic table. Steel is a metal, but if we look at the periodic table, there's no steel on the periodic table. So it's a solution. It's a mixture of metals. Salt is a compound. So if you look up salt, you're going to see it's sodium chloride. It's 2 different elements, and it's always in a 1-to-1 ratio, 1 sodium to 1 chlorine. And water, it kind of depends. Usually when we think of water, we think of H2O. So that would be pure water. Pure water is a compound. If there's only H2O molecules in there, yes. But normally when we get water, we're getting it from different places. So if I get it out of the tap, It probably has fluoride that the city has put in there in order to strengthen our teeth. It might have some calcium, particularly in the Georgetown area, because we have a lot of calcium in the limestone in the bedrock, and that leaches into the water as well. And hard water might have other minerals like magnesium and iron. So we would consider that a solution. We can still see through it. Can't tell the difference looking at water, whether it's pure or a solution. And then we had the example of that pond water in the glass jar. That would be a heterogeneous mixture. So it's got some dirt, some larger particles mixed in. Okay, so the next thing that we looked at, or I asked you to look at, was to talk about the difference between metals, nonmetals, and semimetals. And most of you gave me some definitions, which were correct. There's one key point that I want to focus on that I will get to in just a minute. But one thing I want to look at is that you can also tell whether something is a metal, semimetal, or nonmetal, depending on where it is on the periodic table. And that's going to be really important when we get into ionic compounds and when we get into naming compounds, because whether something is a metal or a non-metal is going to change how we name it, and it's also going to change the charges that are possible. So if you look at the periodic table, usually there's some kind of blocking that indicates these groups. You can see most of the periodic table is made of metals. The whole center portion, the whole bottom portion, and the whole left-hand side, except for that first element, which is hydrogen. Hydrogen is our problem child. Whenever we have an exception, hydrogen is going to be involved somehow. So it sits over there with the metals for reasons we'll talk about later, but it is a non-metal. And then our nonmetals tend to be on the right-hand side. And then there's this diagonal sort of area between the metals and the nonmetals, starting with boron and going diagonally down. Now, aluminum is sometimes considered a weak metal. I would consider it a metal. In this periodic table, they're indicating it as a semi-metal, and there's rationales for that. Okay, so one of the things that makes a difference between a metal and a non-metal is the charge that it takes on. Metals are typically going to form positive charges. Non-metals are going to form negative charges. So if we look over on the yellow portion, the middle and the left-hand side, we see all of these are positives. Some of them are +1, some of them are +2, some of them are +3, but they're all positive. In contrast, if we look on the green side, the right-hand side, all of these are forming negative charges. So nonmetals tend to form what we call anions, or negatively charged ions. So that's going to be important when we start talking about ionic compounds and forming them together. Okay, so then the other thing, and really the key difference between a metal and a metalloid or a semimetal, so you can use both terms, metalloid and semimetals, is the conductivity. So I've looked here at silver and copper, two of the best conductors, and these are measured in what are called Siemens meters. So that's just the unit that we use. But you can see compared to W, which is tungsten, they have very high conductivity. But even tungsten, which is the poorest conductor of the metals, is a lot higher than silicon or carbon. So silicon is in that semi-metal or metalloid area. Carbon is in the non-metal area. All right, so if we look at just that portion down there, I'm going to blow that up on the next graph. Now, notice I'm not taking all of the tungsten thing, just a small little portion at the bottom, about 1/100th of it. Okay, so here's the next chart. 1/100th, tiny, tiny little portion of that tungsten compared to silicon and to carbon. So silicon we still can't see on there. Silicon is a semi-metal, which means that it has multiple forms, what we call allotropes, and one of those forms is an okay conductor. And so it is something that we can use in electronics. Now, the nice thing about being just an okay conductor is we can sort of set up switches where sometimes it's conducting and sometimes it's not conducting. And that's kind of how we can make our computers work. So the fact that it's not as conductive as silver or copper is just fine. It helps us to do electronics. Now you can see carbon there has a little bit of a blip. It's higher than silicon. And you might be thinking, well, why is this non-metal more conductive than the semi-metal? So one of the distinctions is that metals conduct in 3 dimensions. It doesn't matter whether you're going up, down, left, or right. It's conductive everywhere. Carbon is only conductive in 2 directions. It forms these flat layers. And along those layers, it is conductive, but going from one layer to the next, it's not conductive at all. So that's really a distinction that is made. Now, carbon's pretty unusual. Most nonmetals are not conductive at all. So you would really consider them to be even less conductive than silicon. But even though we consider carbon or graphite to be a semiconductor, we consider silicon to be a semiconductor, you can see that compared to metals, they're far, far less conductive. So really that's our distinction between, do we consider something like gallium or aluminum to be in the metal category or the semi-metal or non-metal, or semi-metal or metalloid category, that diagonal line. All right, then, oh, I did want to back up here. Okay, one of the next things I asked you to talk about was a group. And most of you picked one of about 5 or 6 different categories: the alkali metals, the alkaline earth metals, the halogens, the chalcogens, the noble gases, and some of you picked the transition metals. But no one really highlighted where they are on the periodic table. So it's good to make a reference to those. So go back in your notes and make sure that for each of those groups that you listed, you can figure out where it is on the periodic table. Now we call them by their group numbers. The system on this periodic table is a little bit of an old numbering system, but you can still see for the first 2 columns, we call them group 1 and group 2. We just leave off the letter A. And we want to make sure that when we're talking about the characteristics common to those groups, we're going to say things that are unique to that group. So we have group 1 is the alkaline metals and group 2 is the alkaline earth metals. Well, what's different about those? They sound similar, and in a lot of ways they behave similarly. So you can see that all of the alkali metals form a +1 charge, and they're in group 1. And now the alkaline earth metals form a +2 charge, and they're in group 2. So that's one way we can distinguish them. Some other features are that magnesium and calcium, we can have those out in the air. They do corrode a little bit, but lithium, sodium, potassium, those are all so reactive in the air that we have to store them in oil in order to keep them from reacting with the air. Now, on the other side, we have our nonmetals. So what's listed as 7A is what we typically call group 17. So we just add the tens place in front of the number that's there. So group 17 is our halogens. And notice they all have a -1 charge. So a lot of you said they were reactive, which is true, but it's also helpful to know they have a -1 charge. A lot of you mentioned the noble gases, and they're all gases. So that's a good characteristic that keeps them separate from most of the other elements. But notice that we don't have any ions there. Now, some of the other elements don't as well, but in group 18, the noble gases don't form charges. They don't form ions at all. So some of you said they're not reactive or they don't form chemical bonds. Another characteristic is they don't form ions at all. And then the chalcogens is group 16, starting with oxygen. And you can see that they typically form a -2 charge. So, those are some more details that you could maybe put in there. But the main thing there is I really want you for your test to know where these groups appear on the periodic table. So make sure you have that in your notes, even if you just add a little periodic table in there and, write in. These are the names of the groups and where they are on there. And remember, I'm going to let you use your notes on the exam. So that's why I want you to have those there. Okay, I asked you to do the element that corresponded to the date of your birth. Some of you did the month instead of the date. That's fine. I'm not checking your birthdays. My birthday is on the 28th, and so I did element 28 here. Most of you did most of this fine. The atomic number was the the date that you gave, the number. Remember that's equal to the number of protons. Now, when you are listing the most abundant isotope, and you can just Google what's the most abundant isotope of nickel, that number that it's giving you there, so this one, in this case, it says 58 and then nickel, is the mass number. And the mass number is different from the mass because it is a whole number, because we're not actually weighing anything for this. We are just counting how many protons and neutrons and putting that together. So since nickel 58 has a total of 58 protons and neutrons, and I already knew I had 28 protons, I can figure out that I only have 30 neutrons from that. Okay, so the mass on the periodic table is a little bit different. It's not going to be that same number. So make sure you have that distinction. The other thing that I want to point out is that when we use the chemical symbol, which you see next to nickel there, you don't get to pick the chemical symbol. You have to use the one that's on the periodic table. That's internationally agreed upon. Everybody uses the same one, so we don't get confused. But also the way we write it is important. We want to make sure that that second letter is a lowercase, and that way we don't get confused between carbon monoxide, which is a capital C and a capital O, and cobalt, which is a capital C and a lowercase o. So a couple of you, I made a note on your guided notes to that effect, and that's something that I will hold you accountable for throughout the term. All right. I saw a lot of you when you were talking about the elements found in cell phones. I was really pleased. Some of you were thinking of lithium, which is in batteries, and that's great. But a lot of you talked about silicon. And then I had a question about how sand was connected to your cell phones. And so several of you use the terms silica, silicon, and silicone interchangeably, and they're not really interchangeable. So in the center here, we have silicon. You can see it's shiny like a metal would be. And so this is the form of silicon that is most conducting. This is the semimetal. So this is silicon with no E on the end. All right, so that's just an element. All of the atoms in there, by and large, are going to be silicon atoms. Now, silica sometimes refers to glass. So you can see on the bottom the compound SiO2. And so those are little tiny bits of glass, which look a lot like sand. So that's the connection, is that sand, you melt it down and then spread it out, you got yourself some glass. But then you can also have silica gel, in which case we've got the same compound that is making up this silicon dioxide mixed with the gel ingredients. And that's more complicated than we're going to get into. And then we also have silicone. So you can see on the upper right-hand side, there is a picture there of the silicone that might be used in caulking and home improvement. So it's very soft material. And when it dries out, then you can have a seal that blocks water or air from getting out your window or getting between the bathtub or your shower and the wall, and kind of protects your home. The other place you might have seen it is that a lot of times cookware is made of silicone, because silicone can be heated to very high temperatures without damaging it. So this is a strainer that's made out of silicone. You might have seen cupcake holders or cooking things, molds for candy, things like that. Ice cube trays made out of silicone. And so it's pliable. You can, it's rubbery. You can kind of change its shape. So if you have it as a mold, you can get your thing that you molded out of there just by pushing it on it from the bottom. Now you can see on the bottom that it also has silicon and oxygen. It also has these lines sticking up that don't have anything attached to it. That's indicating that we have an organic group, which, as you've looked in chapter 2, that means there's carbon attached to it. And so in this case, it's just one carbon with some hydrogens attached to it. But silicone can be made of a couple of different kinds of compounds. So this is one compound that has carbon mixed in there as well. And the parentheses in there indicate that this pattern gets repeated over and over and over again. So molecules aren't just 3 silicons. they might be hundreds and hundreds of silicons with oxygen and the carbon group in there. So that's what we call a polymer. Okay, so very similar sounding names, but they're not the same thing. One is an element and all the others are compounds. And even among the compounds, we have the hard glass, and then we also have the polymer. So the glass takes on one kind of structure, a crystallized structure, and the silicone has a polymer to it. All right, so those were kind of the key points that I wanted to hit on to make sure that you had in your notes accurately before the test on Thursday. Thank you.